All right. So as I mentioned a few minutes ago, I've made some pretty significant changes to this over the course of the last day. Let me see if I can remember exactly what I did to make sure that I tried to make things slightly clearer where possible. There were a couple places we were not updating the tail correctly. And I renamed current to tail so that we could actually see this working. The easy way, if you're following along, if you just right click on any instance of that, you can just go to where you refactor, rename, and this will allow you to make the change to all associated instances of this. You can see that there's a couple additional tails that now have boxes around them. And as I make changes to this, it's making changes to all of them. So you can very quickly and easily change the name of something and it keeps track of all instances of that. So you don't have to go search for where are all the places I did this and change them all. You don't have to use find and replace. You don't have to use any other tool. Refactor, and you can do that refactoring for just about anything that has a name. So that's super useful. What other changes did I make? I think I made changes to add to actually, I'm not sure if I was actually updating the tail correctly, but now the tail is being updated correctly. Same thing for the add that takes an index and an element. That should now be working. I had to add a couple of cases where if we were actually modifying the tail, we updated the tail. So that's been updated. I don't think too much else needed to change in here. There's another instance of updating the tail correctly. If we remove the tail. I did auto format this at some point. So normally I don't like this style quite as much personally. You're welcome to continue using it, but when you close an if right before you use the else if, you can either have that on the next line or you can have it immediately following it. And if you auto format, at least in Eclipse, it does that. Have people used auto format before in any of your IDEs? I think it's usually something like Control-Shift-F. And if you do that, then it will auto format. So if I do make some really weird change like this, auto format will just change it to be in some particular format that makes sense. I did write a toString though. Did we write the toString? I don't think we wrote the toString. So I wrote a toString. So I don't know, in the past, have you used something like a print nodes function, or have you actually overridden the toString to return a string representation of the object? So overriding the toString. So I did the same thing here, where I needed an index to keep track of everything except the tail, because if we just put this in a loop and add a comma after every element that we print, we end up adding a comma at the end of the last element as well, which is really ugly, and we don't want that. We want commas between each element, but we don't want commas at the very end of or at the very beginning. So this logic makes sure that commas only appear in the middle of the list. We just make an empty string. We set a current node to the head, and we're going to continue going node to node, printing each of those. So if the size is greater than 0, sorry, the size is not greater than 0, let's start there. We just want to say that the list is empty and return that string. Otherwise, we're going to loop through all of the nodes from 0 all the way to size -1. We don't want to go well less than size because that would include that last element. So we're going to concatenate to our empty string, at least what starts out, it's empty. The data, it's important to include the toString because this is generic. We don't know how to print whatever type the nodes contain. The nodes data are of type T. So they could be integers, they could be doubles, they could be person objects or any other custom object. So you want to make sure rather than just printing cur.data, you want to print cur.data.toString, and the toString is defined for integers, for doubles, for every other kind of primitive you might want to use. We'll be using the wrapper class for this, which is why when you actually go instantiate a list like this, you can't make a linked list of type primitive int. Do we know or have we seen the difference between primitives and wrapper classes for the primitives? Is that something that we've seen before? Give me an example of that. I refilled all the ink and all of my pens, so now I actually have choices for colors, which is nice. We'll use red, why not? So one example of this is the difference between an int and an integer, capital I. Does anyone know what the difference between these two data types is? One of them is an object. What does having an object allow that the primitive does not? Yeah, there's definitely, you can do a lot by reference rather than by value. That's true. What does a class contain? Fields and methods. So an int is just a 4-byte, 32-bit set of ones and zeros in 2's complement. So you can imagine this is just a sequence of zeros and ones. There are 32 of these. And if you've seen 2's complement before, this is just a representation of a base 10 integer in base 2 with a little bit of a fun play on negatives. I can go into exactly what 2's complement is if there's interest, but probably hopefully covered in discrete. But so this is just a primitive type. This is just what's stored in memory. It takes 4 bytes. The integer is a class that has fields and methods. So the integer class actually has fields. It's actually just a single field. So I'll draw this up here. It has the value of the integer. So it has like an int value. By itself is these 32 bits. But what it allows us to do is define additional functionality for the integer. So one of the things that you can do to an integer is called the toString method on it. So here we have something like toString, which will handle the logic of int to string conversions for us. We don't actually have to think about how do we convert this integer into a string format. It's handled by the integer's toString. So this is exactly why when you make a linked list of, and you want to use ints, you should actually use the wrapper class integer. And it's called a wrapper because this value here is wrapped by a class. So it has the rest of the class structure embedded in it rather than just having a single value. I did lie, there are more fields than this. Does anyone know, has anyone ever seen or used a field of integer? If you say integer dot something that doesn't have parentheses? Stuff exists like just a final int value. Does anyone have memorized the largest possible value that an integer can be? Have we seen that integers can't go to infinity? There's an upper limit to what we can store in an integer. If you ever want to know what that value is and you don't want to memorize it, just type integer.max value. And this is a publicly accessible field in this class that you can just go grab and use in your code. And the same exists for min value. So you can grab the smallest negative number and use that. So it's extra functionality wrapped in a class. It's all the stuff we would like to be able to do to an int that we can't if we just have 32 bits of storage. We can if we wrap it in a class. And of course, I forgot my eraser and I forgot that it's over there. Ha! One piece of it. So not even fools anymore. Questions on the primitive versus the class representation of an int or integer? So when we say something like .toString, since we guarantee that what we're working with in this linked list is an object, every object has a default toString that can be overridden. So we know that we can print out whatever this is with the toString. And then we move current to the next element in our linked list, and we bump up index so that we know when we're going to be done here. The final version of this that we're going to do once we fall out of this while loop is one more time, we're going to print the very last element in the list, but this time without the comma. So that's just visual, make sure that there isn't a dangling comma at the end of our list. Then I went ahead and implemented the iterator as well, because I didn't really want to live code the iterator. Stuff can go wrong. I wanted to make sure that I wasn't getting lost and wasting people's time. It took a little while. I made a couple mistakes. It happens. So you can see that one of the changes I made at the very top is I now implement iterable of t. The iterable interface just says that we now need to have an iterator method that returns an iterator object. And remember that the iterator object is just an object that's used for iterating over a collection when we also want to be able to add to that collection or remove from that collection while we are iterating it. So while we're in the process of going from node to node, we want to be able to put a node in the middle of it. We want to be able to take a node out as we're going through it. So we just need to add iterable, and then we need to make sure that we implement the iterator. And it's a single line, so it's not actually too hard. We're going to return a new list iterator of type t, and the list iterator takes a parameter that is a linked list. Basically, it wants to know which linked list we want to get an iterator back for. So we want to pass it this object. We want a linked list iterator over the current object, the object that we are currently modifying. Now, list iterator is going to work for you until you actually go make it. So you can see that up here, I have the list iterator class that I wrote. So we're going to start going over that. So if you type this and it doesn't know what a list iterator is, that's perfectly understandable and expected because we haven't implemented it yet. So now we need to go define the logic for what it means to be able to make the associated modifications to the linked list while we are iterating it. So let's go take a look at that class. So list iterator is also going to implement iterator. We have 3 fields. We need to be able to store nodes for the current position, because as we're iterating, we're going to have a current node, the current position in the linked list that we're going to be looking at as we iterate and go from node to node to node to node. We also need to keep track of the previous node, because if we decide to remove in the middle of the list, we're going to need access to that. So we're kind of keeping track of both of those things as we go. We also need to know which list we are iterating over, because the list iterator isn't an inner class to the linked list. Note that it could be both the node class and this list iterator could be inner classes inside of the linked list class. But I actually don't want that in this case. And the reason for this is that we're going to be implementing additional linked lists. So this linked list that we have is just a singly linked list. Your assignment is going to be to implement the doubly linked list and circular linked list that you've probably seen and done some stuff with, but now you can use my code as a base. And the idea is that we want to implement the list interface that we already have, but now additionally implement a couple other types of linked lists that also implement this list interface. And that way we can start using polymorphism. We can start coding to this interface, not caring if the underlying implementation is a singly linked list or a doubly linked list or a circular linked list. Each of those classes will handle the associated logic of whatever the user wants to do. And all of that logic is embedded in this interface. It's just the name of the instructions. The logic for how to carry out those instructions will be slightly different between those three linked lists, but the interface won't care. It'll just say which type of object is it, call the associated method for that object type. If it's a doubly linked list, call the doubly linked list method for add and remove. And that has all of the logic embedded inside of it for how we're going to handle doing that with this list. To make that change, there was one other change that I made in linked list. If I scroll up to the top, you will note that I changed the access modifiers for linked list from being private to being protected. I went over this in 2.12 yesterday, but not everybody's in that class. So protected means that it's publicly visible within the same package, and private for any class that is outside of that package. So what that means is if I write some kind of program somewhere that uses my linked list, that imports it, I will not have the ability to modify the head or the size or the tail. But if I have a list iterator, the list iterator is going to need to modify these things as we add or remove from the list while we are iterating it. So we actually need access to those things to be able to do that modification. If it's protected, it's publicly accessible from the list iterator class, but it's private from anything outside of this package that is trying to call it. So protected is the appropriate modifier to use in this case. Does that make sense? All right, back to the list iterator. So the constructor for this is going to set the current position to null and say that the list that is the field list should be the list that is passed in as a parameter in the constructor. It's tempting to set this position to the head of the list and swap this order, but it'll actually give you some issues. Because the very first thing that you need to do when you use a list iterator, remember that the very first thing you do cannot be to remove, it has to be to call next. And the first time that you call next, it needs to give you the head of the list. So because of this, we're going to initialize this to null, such that when we call next for the first time, we actually get back the head of the list. All right, the has next. So remember that the iterator has 4 methods that we want to override. The first is has next, the second is next, and then we also want to be able to add and remove in the middle of that iteration. So those are the 4 methods that we need to make sure that we implement. Has next just tells us true or false, yes or no. Is there another node for us to grab to go to the next one? And if you think of something like a for each loop, this would be what determines in the for each loop if there's another iteration of the loop. So we want to say, if the current one is null, then we want to return whether or not the head is null. If the head is null, that means the list is empty. And so we should return the opposite of whether the head is null. Does that make sense? Otherwise, we take the current position and we're going to query its next and check whether or not that is null. If pos.next is null, then we want has next to return false. There is no next element. If pos.next is not null, then we want has next to return true, that there is another element for us to go grab with next. So that's just the logic for has next. Here's the logic for next. So if we call next and there's nothing for us to go grab, because we haven't checked it with has next first, we need to make sure that we throw the appropriate no such element exception. I think I changed a couple of the exceptions as well. I'll go back to that. I also upload this code to Canvas so that people can just grab this exact code and run with it since it does work. So next is going to return the object, the data of that. And the idea is to grab the next node and store that in the current position. So if there is no next element to grab, we should throw a no such element exception. If that's not the case, that means there is another element. So we want to first update our previous to the current position, because we're going to be moving forward to the next thing. So we can first change, we have previous, and we have position. We want to update this to be this and this to be this in our linked list. So we know for sure that we can update previous to position regardless of whether or not it's null, because we're not dereferencing it. However, if the current position is null, that's true the first time we call this, then we want the position to be the head of the list. Otherwise, there is a next element and we can go grab it. So we set position to position.next. Once we're done with all of that, we return the data. Questions about next? All right, the last one, and this is far and away the most difficult because remove can't be called twice in a row. You have to remove and then next, and then remove and then next, and then remove and then next. There has to be a current node. Pause cannot be null if we're going to remove pause. That's just the necessary logic that we need in order to make sure that we can do that removal in the middle of the iteration. There's no way to know for sure, be able to do remove followed by remove. So a lot of iterators actually don't implement remove. If you just wanted to be able to add in the middle of the list, you would just implement add, and that would be the end of it. And then you could throw an unsupported, what is it called? It's an unsupported something exception. So here's remove. We need to check whether or not either position is null or the data stored there is null. So we can have a node that exists that has null data. So we need to check for the entire node. And we also need to check whether the data of that node, if it exists, is null. This uses what's called short circuit evaluation. Have people heard of the concept of short circuit evaluation? Basically, we're dereferencing pause right here. If pause is null, this will throw a null pointer exception. That's not good. We don't want that null pointer exception. So how is this line actually working if when we check this, we're not, then it would throw the null pointer exception? And the answer is because Java has an intelligent fail first system. When you have a Boolean OR like this, quickly draw out the truth table for the OR. We have, I don't know, we'll call it position 1 and position 2 that can either be true and true, or true and false, or false and true, or false and false. And for the OR, this is true, 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 and false, right? So what do we know if the first element happens to be true? What can we determine about the value of the OR if the left-hand side of the OR happens to be true? It's always true. Do we even need to check the value of this right-hand side? No, that's exactly what Java does. So if this is true, pause is null, it's not even going to run this. And this entire thing is going to be true. So even though there's the option of the ability to dereference null there, we don't actually access it if the left-hand side is true. But that's what keeps this line working no matter what. Questions about that? Have we seen truth tables before or no? how to visualize logic that way. That's usually a discrete topic. I don't know how many people have taken or are taking discrete. So that's why that works. If either one of these is true, we'll throw the illegal state exception. Only if the left-hand side is false do we check the value of the right-hand side. If either one is true, then we throw the illegal state exception. If neither one is true, then we move on. So if the position is the head of the list, then we need to call remove on the head of the list. Easy enough. And since remember that we said that everything was, I guess remove is publicly accessible. But even if we were accessing a field here, we could do so because it's protected. Yeah.
So the order is very important for them.
Yes, if you flipped the order of this or, you would occasionally get a null pointer. So even though ors are commutative like that, you can actually flip the order and it doesn't change the end result. In programming, sometimes we actually have to think about the order of our ors. It's a great point. So we can remove, note that remove takes care of the size for us. This is a very easy thing to mix or to miss or mess up. Remove in the list, in the linked list class, if we look at our remove, and it's remove at an index, takes care of the size for us. So we don't additionally want to remove the size when in the list iterator, we are calling the lists remove. Otherwise, we want to set preves next to pause next. This is exactly the same diagram that we drew yesterday for the remove. We want to make sure the previous next points at the current position's next, and that deletes the current position. Let me give you one last look at that just to make sure that's clear. We have preve, have pause, and we have some node that is after that potentially. We're going to say preves next, which currently points at pause, needs to point at pause.next. So that replaces this arrow with that arrow. And now since there's no reference to pause, there's no way to access this node anymore. There's no reference to this node object. Java's garbage collector will come and collect it, freeing that memory, and now it is no longer part of our list. All right, I probably should have flipped the order of add and remove. I always like to tackle the hard thing first, just a personal thing. So add, a little bit less complicated. We're going to make the new node that we want to add. We know because add passes in the data that we want to add to it, we need to make the node that contains data, but we also don't know where it's going to go yet. So we're going to make sure that its next is null. So that's just the two elements of the constructor that we want to call here. We have a couple checks to make. If the head is null, that means that there's nothing in the list. And note that this add is not overridden because maybe someone can tell me here, why do we not have an index, an add with an index? We only have an add with a data. Why does that make sense? Same with remove. This isn't the linked lists add or remove. This is the iterators add or remove. And remember that an iterator is like a for each loop. There's a current position as we are going through the list. So this add and remove says at the current position in this iteration, add here or remove here. There's nowhere else to look at. There's only the current position. So we're either going to insert where we currently are or remove where we currently are. So there's the only two methods that we need. So if the head is null, then when we add, we know that's where we are. Otherwise, we need to look at the positions next and check if that is not null. If it is, then we want to link up this node's next with this pause's next. If that's not the case, then we're at the tail, so we can add to the end. Those are the three main cases. We're either at the beginning, we're in the middle, or we're at the end. Regardless of what we do, the current positions next needs to be set to the node. And since we're not calling the lists add at all, we need to make sure that we can bump up the list size. And here we are publicly accessing the lists field. And this is why we set that to protected, because this is in the same, package. We can publicly access the list's size. If that were private, this would break. Any questions about any of the iterator methods or what the iterator is doing? This is just kind of a general approach for how you would make an iterator over any collection. We need to make sure that we have that associated logic so that we can, in the middle of an iteration, make changes to the list. That's just a nice thing to be able to allow the user to do. So if we go over to our driver, we can kind of test this out and make sure that it works as you would expect. So rather than test this with integers, I tried to test it with a double because that's just fun to do. And remember that if you are going to make a linked list, you want to use a primitive, you want to use the wrapper class of that primitive. So rather than using a lowercase d double, we want to use an uppercase d double. That's just the wrapper class for double. Does anyone know any of the features of the wrapper class double? There's a field double dot nan, or a const, I should say a constant. Because sometimes you end up with something that's not a number when you do things like divide by 0. So you can actually set the value of this double to not a number. It's a special value that the double class can take that the primitive double cannot. And that way you can do things like check if it's nan. A primitive double just is nan. So when you go try to print it, you get not a number. But on the other hand, you can say if this double is nan and use that as error checking if you use the wrapper class's double. All right, so we're going to print the list at the very beginning. What should this print give us?
List empty.
List is empty. If we look back at our linked list and at our toString says that if size is not greater than 0, then we should print list is empty. So that's what we expect. We will add 1, print the list. We should see 1.0 with no comma when we print the list again. We go to add 2. Now we should have 1.0, comma 2.0, no comma after the 2. We'll add 3, 1.0, comma 2.0, comma 3.0. We'll then go to remove the end of the list. This should update the tail correctly. So if you're thinking of good test cases for a list, make sure that you're modifying things like the head and the tail, because those end up being those difficult side cases where if you don't do that correctly, then things might not work quite as well as you hope them to. We'll print out the list again. We should be back to 1.0, comma 2.0 with no comma after that. We'll add a couple more things just to test adding after removing and making sure that the updates correctly. We can then print out the list.size. Here we should see 4. We added an element, added an element, added an element, removed an element, added an element, and added another element. So we should be back at 4. Finally, we'll print the toString one last time to see, hopefully, 1, 2, 5, 5. We're going to make the iterator. And we're going to go through and delete all of the elements as we are iterating. So while the iterator has another value to delete, we're going to grab the next. The first time that'll grab the head, and then it will remove that. Loop around, grab it, remove it. Loop around, grab it, remove it. So if we run this, it says that there are errors, but there are not. It's lying to me. The values that we see here, list is empty, 1, 2, 1, 2, 3, back to 1, 2, 4 elements in the list, 1, 2, 5, 5, like you would expect, and seeing the list is empty. Let's play around with the debugger a little bit, just to see an example of that working, so that you can test how do you see the internal state of your program while it is running. To do this, we want to make sure that we add breakpoints to the code. So you can do exactly the same thing if you have any difficulty transitioning any of this logic to IntelliJ, I can help you with that. It's basically the same between the two, but let's go into our linked list. If we look at our linked list driver, where is a point in this code where you'd like to actually see it doing the underlying logic? Yeah, when we remove might be nice. So I actually already have a breakpoint here, but usually there's a bar along this left side. If you double click inside of that, you'll make this little dot. This barely shows up, but now there's a dot on line 15 that tells us there is a breakpoint there. Instead of clicking the play button or the run button, you can go click the debug button, which is going to be separate. You click the debug button, and it should have opened up the debug perspective. And it did not. It did last time. Easy way to bring up that, forget exactly how to do it. Perspective, open perspective. Maybe what I do is I reset the perspective. That possibly will work. I reset this and then debug. There we go. So this is what I would expect to see, where we care a little bit less about this left-hand side. We care much more about the right-hand side. So now the code is right on this list remove. We've done everything up until this point. So if you want to figure out what is going on inside of this program, we have the current state of our program right here. You can see that we have this list, linked list. If you click the arrow, you can bring it down and you can see all of its fields. So you can see the head and the tail and the size. The size is currently 3 because we've added 1 and 2 and 3. If we look at the head, you can see that the head is a node that contains a data segment and a next segment. I know this is super small, I apologize, but you can reveal the data, and the head has value 1.0, which is what you would expect at a linked list of 3 elements that contains the 1 and the 2 and the 3, the first things that we've just done. So the head contains 1.0, and the next is a pointer, a reference to another node that has data 2, which has a next to a data with a value of 3. And note that I can't expand the next because its value here, it tells me, is null. So this allows you, without printing anything out in your program, no writing print lines, to see at a particular point in your code what the value of every part of the state of your code is. This is the equivalent of after the print line there, before the list.remove, typing system.out.println head.data, system.out.println head.next, system.out.println head.next.data, etc. All of those print lines are contained within this data that's on the right-hand side of the debugger. So incredibly useful for making sure that your program is performing the way that you expect. As we look at all of these things, we see that the values are what we expect. If they weren't what we expected at this point in the code, we would know that something happened before that. Now, the important things that you can do are these step into and step over buttons that exist on the top bar. These appear whenever you are debugging that help you to now be able to execute your code from this point line by line. And this allows you to see how every single line of your program is updating all of these values on the fly, line by line. So list.remove is a function call, so we want to step into that function call. If I step over it, it's going to do this entire list.remove all at once. But let's say I wanted to check and make sure that every line of this remove was working correctly. That's why I want to step into the remove so that we change the scope into the method that is being called. So we will step into the list.remove, and that takes us to, yes, a couple things happen first. So I'll step over that and step back into the remove. And now you see that we are actually in the remove that got called. So it's removing a particular element, not removing at a particular index. When we remove 3.0, 3.0 is a double, not an index. So it calls the remove that takes the element. We can step into this if we wanted to watch and see it throw this null pointer exception if the past element was null. But we know that wasn't the case, so we can step over it, and we see that, sure enough, this if did not turn out to be true. So the current line that's being executed is this if is empty. So now we could step into, if we wanted to watch the is empty return true or false. We can step over if we just want to see the result of that. If we have reason to think that our is empty is working, we don't need to see it work, so we can step over it. This allows you to really isolate where you think the bugs might be in your program. If you think there's an issue with is empty, you should step into it. If you don't think there's an issue with it, you should step over it, but then still go back and verify that the value of everything that you expect is still what you expect. If it's not, then there was an issue between the last step where it was correct and the current step where it is not correct. You can continue. This will set a query equal to the head. If we step over this, we will see that now there is a new field listed here. This tells you the associated memory address of that node, and we can look at the data and next of the associated query. Since we set that query equal to the head's information should be the same as query. Note that they're stored at the exact same memory location. We talked a little bit about shallow copy versus deep copy the other day. So when we say node query equals head, nowhere are we saying new anywhere. So this should be a shallow copy. We have two references to the same node object. So they should be stored at the same memory address. You can use this to debug things like, did I actually deep copy this when I meant to deep copy this? If you do, they could have different memory addresses. Since they have the same memory address, this is correctly shallow copying the head into query. Stepping over this, we can look at this while not query.data equals element. Now here's again where we want to step into, because we're going to make sure that we want to iterate over this loop and not just end the loop. So we're going to step into the loop and see, we can actually watch and see the equals method run. This is the actual source, Java source code for the double. So this is going to run the dot equals to determine if these two objects are the same. We know that works, so we're not going to worry about it. So the equals has now returned, and this will tell us now whether we go into it or not. And sure enough, they were not equal, so that's why we went into the loop. I'm not going to do too much more of this probably, because this is just a useful, how do you use the debugger? What is the associated logic that you can think about while you are using the debugger? But it is an incredibly useful tool that will save you a ton of time. Because it is so easy to use, I highly recommend that people, as soon as you finish a method, as soon as you finish even just a few lines of code, go verify that it works. Have some driver program that you have for some basic tests. Or if you are in 212, you will learn how to write unit tests, write some unit tests alongside your code. And every time you write a few lines of code, make sure that you're running those unit tests, or make sure that you're running your driver file that contains some of the tests that you're running on it to ensure that it has a basic level of functionality. Any questions about the debugger? Any other fun things that I can show off? Questions about how to use it, when you would appropriately use it, how to save time when you're programming? When you first start programming, you spend about 10% of your time implementing code and 90% of your time debugging. The goal is to flip those. The goal eventually is to spend about 90% of your time writing code and 10% of your time debugging. The debugger can greatly help with that, as can not writing so much code that there are 50 errors inside of the code that you've written and you have to go figure them all out without having the shell around your error working. If there's only one error, everything else works. If there are 50 errors, you reach the breakpoint in your code and there's already stuff that's wrong. And trying to isolate and figure out what individual things are wrong when there are multiple things wrong is a much, much harder problem. The complexity of that just increases exponentially as you get more and more errors in your code. So test early, test often, and that will make sure that you are starting to flip that implementation debugging time. So my plan, assuming there are no questions. My plan to assign today, and I mentioned on the syllabus, I like things to be due Wednesdays, so Wednesday night, we will have this due. I will just upload this code. I will upload an assignment that will have you implementing this same interface that we have here, just implementing this interface to create a doubly linked list, a circular linked list, and you can absolutely just copy and paste most of this code, make the associated changes that you need to. Part of it will involve some documentation, so I will describe how to document this code and document that code, so that we make sure that you get some practice getting some good documentation standards in. And I can answer questions about this process. Please try to get started with it over the weekend, but I can answer questions about it either Monday or Tuesday or Wednesday ahead of its deadline on Wednesday. I don't anticipate this being crazy difficult because for the most part, all of the hard work we've done in class, it's just thinking about what are the changes between a singly linked list and a doubly linked list. What's the change between a doubly linked list and a circular doubly linked list? There are a few difficult things about that, but you also hopefully have some experience with that from 211. If you're one of the couple people in the class who are taking it concurrently with 211, feel free to reach out to me. I would be happy to meet with you and work with you to help you better understand the assignment and make sure that you can be successful. Questions or concerns before we adjourn for the weekend? Awesome. Have a great weekend. Do something fun for yourself. Have some fun. And I will see you back here on Monday.